So coming to the various modes of failures in composites, the very basic or fundamental modes we can identify is matrix cracking. The very basic of composite is made up of matrix. So once the matrix starts cracking under the given loading, it will initiate various other modes of damage. So the first mode of failure is generally matrix cracking. So further, it will give rise to fiber matrix debonding in the composite, which will further this happens in a lamina level. So before coming to lamina level, matrix cracking and fiber matrix debonding are first mode of failures. So once we have failures in lamina, so this will again propagate to subsequent laminas by in interlaminar delaminations. Uh, this leads to fiber fracture and complete failure. So as you can see in the right hand side, we have a small representation of various scales. So as we all know that matrix and fiber makes the core ingredient of any composite material. Analyzing this any component in this scale, we call it as micromechanics. So we use computational micromechanics to analyze some of the composites in this scale, and from this scale we move towards a lamina and then a laminate. So this forms an intermediate scale called as mesoscale mechanics, and then from there we form a component, subcomponent, and structure. So here we use next scale called as macromechanics. So this is, we cover in computational mechanics schemes. So in micromechanics, most of the uh, ingredient of composite will have effect of nanomechanics happening into the fiber and matrix system. So nanomechanics in terms of polymerization and its effect can have a huge influence in the initial stages of composite materials. So various scales are required to analyze these composite materials. So why do we need different scales of analysis? Because the constituents that are important that are used in the composite material have to be understood in a micromechanics scale, whereas the overall composite structure and its behavior has to be analyzed in a structural scale. So we need a bridge that will relate the micromechanics and the macromechanics. So how do we bridge this gap is by using various different tools. It could be analytical tools, it could be finite element based tools that we analyze and take inputs from micromechanics, use these inputs into micromechanics scale and analyze the overall structure. So by definition, what is micromechanics is the study of composite materials which assumes it has a homogeneous property. So this approach is good for analyzing large scale structures, but it does not predict the stress levels at micro level, and these stresses, if we are able to predict some of these stresses, but these stresses will not be accurate from macromechanics scale. So then what is micromechanics? The study of composite materials by understanding the interaction between the constituent materials at a microscopic scale, we call it as micromechanics. So this approach will help us in understanding the failure mechanisms in the composites, as well as computing the material properties theoretically. So whereas this approach will be difficult to use for large structures because it has a limitation in terms of computational efficiency. So this micromechanics will help you in understanding the failure mechanisms in fibers. Basically, when the fibers are subjected to tensile loads, buckling and splitting, etc. These are various failure mechanisms that can happen in fibers. Whereas in matrix, again based on the load subjected, the matrix failure mechanism will be different than fiber failure mechanisms. So further, the interface between these failure mechanisms can also be understood properly by analyzing the micromechanical behavior. So with this understanding, the fracture toughness, fatigue life and strength of these composites can be analyzed very easily, and this forms the basics for macro level evolution of elastic properties. So however, the micromechanics cannot be used to understand the structural behavior of a very large structure because computationally it will be very inefficient. So coming to comparison of micromechanical analysis, some of the advantages and disadvantages of micromechanics. Macromechanics is in micromechanics the computation will be efficient, and the experimental testing will incorporate all the in situ effects such as interface damage, residual stress, etc. So when we say experimental testing, means we will be testing at a component level at macro scale. So it could be based on standards such as ASTM or ISO standards. So these testing procedures will define what should be the dimensions of the sample and loading rates of the sample. Based on this, the experimental investigations will be done at a macromechanical level. And alignment, the other advantages of micromechanics is alignment and ply level designs are already involved because the thickness of the sample that will be used in micromechanics will be somewhere in millimeter ranges. So it will involve the designing of the composites at a ply level. So micromechanics works well when we have a fiber dominated situation, such as the loading direction will have good amount of fiber, whereas matrix will be used mainly for bonding purpose. And this will also help, works well when we have a linear system in an isothermal regime. So again, when we have a non-isothermal regime, the thermal effects that are indulging a lot of mechanical stresses will also depend on the fiber and matrix properties at various length scales. So major disadvantage of macromechanical analysis is the anisotropic behavior that are used that comes in composite materials. So these constituent theories should be known because it involves the properties at different directions in the composites will be different. So we need a anisotropic constituent theory here. So further complexities will be there when we have tension compression combination, creep when it is having creep behavior in these composites, and other will be multi-axial and hydrostatic interactions that will happen. So this understanding at a macromechanical level has some challenges. So whenever we are doing this analysis, so when there is change in layer or volume fraction, or there is any change in the processing of the composite, so there is always a requirement for recalibration. For example, when you change the layer of the composite, and we had done some computation, or we had done some experiments in micromechanical scale, and we change up any layer sequence or volume fraction or any processing. So again, we need to recalibrate or retest these materials, because it will have a significant change in its properties. And most of the time when nonlinearity is involved, so most of the time phenomenological based models are used at micromechanics level, which may not be correct always. So in micromechanics, this is one of the major disadvantages. And in terms of mathematical forms, we have something called internal state variable that comes in thermodynamical principles. So these are not used in micromechanical and composite materials, because that is used mainly in monolithical materials such as metals. So when there is an isothermal loading, this will certainly affect the composite material. So this is also one of the major disadvantages when we go for macromechanical analysis. When we analyze in scales of micromechanics, the major advantage we'll be getting is we'll be able to capture the physics involved in the deformation and the damage at a very fundamental level. So this will also capture various states of multi-axiality involved in stress and strain states, as well as isothermal states, whether it is isothermal or non-isothermal conditions. These states can be easily captured in a micromechanical scale. So this is mainly because we'll be utilizing a simpler isotropic constitutive law models for fiber and matrix systems. So because of this simplicity, we'll be able to capture various complex conditions that evolve in the composite material. So it is again, we will be using a very fundamental failure criteria for defining the failure in matrix as well as fiber system, but this will help in analyzing a complex failure in composite material in micromechanical scale. So obviously we will be seeing the effects of this composite at a micro scale, so microstructural effects can be easily captured. So this also gives an advantage, like what if the material design of the material is changed, what will be the implication of the overall structure when we do it in micromechanical scale. So we will be able to handle any changes in scenarios, because this can be adapted easily when we go for a micromechanical scale. The major disadvantage of using micromechanics is it is extensively expensive when we go for modeling a complete structure in terms of micromechanics. So if we, and another major disadvantage is we need to know the constituent response of the individual constituent material which are used, and the overall composite will not have the same properties as fiber and matrix. So we need to have a validation testing, which is separate than the validation that is required for individual constituent material. So there is always a requirement for recalibrating any other in situ effects that are possible in the composite system. Interfacial behavior is always an unknown when we go for micromechanical scale, because we do not consider component level analysis or a subcomponent level analysis here. and the technology readiness level is lower in micromechanics. So with this basic difference in analyzing of composite at various scales, now let us see what are the various approaches that are used in micromechanics. So the first approach is based on mechanics of materials. So I hope most of you are aware of strength of materials that you might have studied in your bachelor's. So these methods are based on these mechanics of materials approach that are used to define the micromechanical properties of the system. So the second approach is based on elasticity based approach. So this is little bit advanced approach as compared to the mechanics based approach. So some of the schemes that are used here is self-consistent scheme and a generalized consistent scheme, differential based scheme, and we have most widely used method for particulate composites is SLB equivalent inclusion method. Here we have a Mori-Tanaka theory, which is used to define the interaction of reinforcing material and the metric system that combines with uh, that is analyzed together for an applied load in a micromechanics scale. Further, one of the most advanced method used in micromechanical models is method of cells. Here, representative volume element of composite material is used, and the representative volume element will be analyzed to obtain the various properties of the material, and that will be used for further analysis. So as I told that there are various schemes. So at the top left you can see a representation where we have a inside fiber material and surrounded by a matrix. So in elasticity based approaches we assume that it will be in a cylindrical coordinate system. So using this assumption we form a analytical solution by considering these forms and obtain solution based on elasticity to form. This forms the basic of elasticity approaches, whereas in mechanics based approach we assume the condition as seen in top right hand side. You can see that we have a matrix layer and a fiber layer subjected to a load sigma 1, and based on this simple definition we will define what is the strain that is evolved in the material for a defined length, yeah, L. So based on this approach we will be able to find out the stiffness and the strength of various composite materials. So in the bottom you can see that there is a representation of an RB. We consider a small portion of this and call it as an unit cell. The unit cell basically represents a small portion of infinitesimally small portion of the composite, which has all the basic ingredients of the composites. We analyze the unit cell, and the overall properties of the composites can be analyzed from considering a small portion of the composite. So this forms the basics of method of cells. So in top left, bottom right, you can see we have a small representation of repetitive unit cell. So from the unit cell we will form the main geometrical representation of the composite material. All these schemes are mainly for long fiber composites and particulate composites. So there are various methods that are used again for some of the other composites that are woven fabrics or satin textile based composites. So coming to next, we will be analyzing how the properties are changing for composite materials for varying volume fractions. So here you can see the left hand side image shows the variation of longitudinal stiffness for varying volume fraction in a glass epoxy system, whereas right hand side you can see that the variation of transverse stiffness for varying volume fraction of a glass epoxy system. And you can see that the orange line in the left side represents the Weigott and method of cells based prediction of the composite material, whereas the pink one represents the Roos model. So basically these are the two models which forms the upper bound and lower bound of the micromechanical models. So any composite material, if it is having a volume fraction ranging from 0 to 1, then the predicted longitudinal stiffness will be in the within the bounds of these two curves. So these are the theoretical predictions. So on top of this, the experimental data will be used that will give you the exact data. But when we use these two models based on the approximate theories, so we can use approximate theories that will be giving you right condition. As you see that there is a lot of variation when you use upper bound models and lower bound models for predicting properties. This is mainly because the assumptions and the conditions that are used in developing these models. Nevertheless, when we have the complete understanding of these models, it will be easier for us to choose which models has to be used and which property has to be which model has to be used for predicting which type of properties and how these varying volume fractions can be captured from these models. So this is again a representation of varying Poisson's ratio with respect to volume fraction in glass epoxy systems. So again, you can see there is a lot of difference from various models that I have mentioned earlier. So next again, this is again some of the properties, mainly the shear modulus variation with respect to volume fraction. So these are basically the bounds that will give you the elastic properties. Similarly, these are just the few of the properties that are shown, whereas with micromechanical models you can also get some of the strength-based properties, as well as you can also analyze how the failure and mechanisms that are involved in the failure that will help in designing the composite as well as enabling individuals to improve the designs. So with this basics, I'll just move on to the current trends in composite materials. So there are various advanced composites which are multifunctional in its design. So when the advent of composite materials was happening, so it was developed with the main function that it will help in taking up one kind of function that was basically improving the strength and load carrying capability with the of the composite. But nowadays some of the advanced composite comes with multifunctionality, that is, it can have good strength as well as it can also have a secondary function such as thermal management also. So one such example is sandwich structures, where honeycomb structure is used. It will give you good strength as well as it will have secondary or tertiary functionalities. It can be thermal management, it could be electrical or electromagnetic insulations, acoustic insulations. So a composite can have multifunctional um, design by in its nature. So developing this multifunctionality again requires a lot of insight into the micromechanics and its behavior. So another trend that is happening in composite materials is use of nanoparticles in composites. So they form nanocomposites. So we use various nanomaterials that are available are carbon-based CNTs, graphenes, as well as in ceramic-based nanoparticles, ferrous-based nanoparticles. So these nanoparticles are mixed thoroughly in the metric system and then used in the composites. And when you use such composite materials, again the uh, fracture behavior or the load carrying capacities of these composites can significantly change when you use nanoparticles in these composites. So understanding of these nanocomposites is again requires a good understanding in micromechanics. So we have smart composites where various shape memory alloys are used, shape memory alloy polymers are used. What happens in smart composites is they can adapt to various shapes and change their size, and they can remember their size and shapes by if it is activated thermally or electrically. So such composites are highly used in adaptive structures as well as they are used in sensing and actuations. So smart composites also have embedded sensors in it. So not only it has um, capability to have good structural design, but also it can have a good sensing and actuation capability. So some of the smart composites use strain gauges that are embedded in them. So some of them use piezoelectric materials that are embedded inside the composites that gives its ability to sense various parameters such as strain, temperature, etc. So another major trend that is happening in composites is development of 3D composites. As we know that composites are mainly made up of fiber and metric systems. So the fiber, which is usually two dimension, is are now being analyzed in a three dimension, and additive manufacturing using 3D printers are used to make this three-dimensional fiber systems and then use epoxy on top of that to form 3D composite structures which will have superior strength because these are again tailor-made for the applications. So some other trends involve using artificial intelligence and machine learning to read composite properties and its estimation, because most of the predictions of composite materials requires a lot of computational time or experimental facilities. So that can be overcome by using some of the advanced techniques such as artificial intelligence and machine learning that are highly used in neural networks nowadays. So with this, some of the job opportunities that are existing in the field of composite materials are materials engineers. Mainly, they'll be involved in developing composite materials in R&D centers, scales, mainly in industries. And then in the CAE, that is computer-aided engineering. So we have a very specific job profile where composite analysis is highly trained people are required. Whereas again in testing and evaluation side, materials engineers with a good amount of knowledge in composite materials are highly required. So these are mainly in industrial centers. Whereas if you are looking for R&D sectors, you can also see there are a lot of requirements in research scientists and research fellows in various R&D centers in industries, as well as various R&D labs across the world. So if you are looking for various academical opportunities, so you have various GRF, SRF, you can enroll into PhD positions, go forward for a postdoctoral fellowship, and have a career as a faculty or a professor at various universities. So these are some of the job opportunities in the field of composites. So this we come to an end in this short webinar. So that's it from my side.